Thank you all so much for having me. It's always great to be here at Virginia Tech. This is my second time to come here. The last time I was in Blacksburg was about 10 years ago, and really it's a treat to come and visit with you all. Dr. Galbraith has been a fantastic host, and again, I'm looking forward to showing you all the film tonight, so please come out to the Lyric tonight at 7 o'clock for that. So, portable X-ray fluorescence is an instrument, it's a proximal sensor, and it's really come to define much of my research career over the last decade or so. And as John has mentioned, I've published dozens of papers on this in journals all over the world, and we've done research with this instrument all over the world in all kinds of different applications. So I want to talk with you this morning about some of those applications and some of the findings and maybe get you brainstorming as to some ways that you could use this technology as well. So before I get to that, let's step back in time a little bit and first talk about how soil survey work was done in the United States. Realize that, for decades and decades, people have been looking at the geology of areas when they start to consider the soils that will develop from those rocks and minerals. And so we've mapped soils based on geologic formations and landforms and lithology. And here you see some of the very early reconnaissance soil survey work going on in Texas back in 1922. This reconnaissance soil survey in South Texas with George Coffey as one of the authors was printed in 1910. Well, one of the major contributors to soil concepts and how we understand soils today was Curtis Marbut. And Marbut had what he developed was called the normal soil concept. And it really identified and differentiated two major types of soils. The pedicals, containing large amounts of calcium carbonate. These are mostly found in the western United States. And the pedalfers, which you would have here on the East Coast, containing large amounts of iron and aluminum. And over here you see in this photo some of our petrocalcic horizons that we would have out in West Texas with this kind of laminar coating and pissoliths of an extreme amount of calcium carbonate. But even back here in this early stages of soil survey, I want you to recognize that we have calcium in here and aluminum and iron. They were already starting to break soils out and differentiate them based on elemental composition. Well, in the 1950s and 60s, we saw rapid advances in soil chemistry, soil physics, soil biology, and mineralogy. And we really had a shift in soil survey from qualitative descriptions, going out and describing chestnut soils or red soils, to a much more quantifiable system. In the 1960s, we had Dr. Guy Smith commissioned to develop a new system of soil classification based on quantifiable data. And this bears itself out today if you look at the European system for classifying soils, the World Reference Base, which is a book about this thick, versus U.S. soil taxonomy, which is about this thick. Ours is about 900 pages. And the reason our system is so much thicker and has a lot more heft to it is because we have all of these discrete quantifiable classes saying, in order to have this kind of horizon, you need this thickness with this amount of property and this position of the landscape. We very precisely map all of that out in quantifiable classes. Well, from the 1990s to the present, we've used all kinds of technology to advance our modern soil surveys. Of course, every soil scientist now, when they go out to map in the field, you got your description kit and your soil knife and your water bottle, but you've now also got to have a GPS with you everywhere you go because we want to know exactly where we are on the land surface. We've used a lot of proximal and remotely sensed data. The reason that we've really seen this take off in the last decade or so is this data is very easy to acquire, it's inexpensive, and it's very powerful. And so we have things like infrared satellite imagery, visible and near infrared diffuse reflectance spectroscopy, ground penetrating radar, electromagnetic induction, what I'll be talking about this morning, the field portable X-ray fluorescence spectroscopy, then even in-situ sensor arrays. And there's more, beyond that, lots of different things that you could look at, neutron probes and whatnot. All of this data that we have is assembled today into what we call Soil Survey Geographic Data, or SURGO data. And it is one of the most powerful soil survey products in the world. Probably the other countries that kind of approach this would be China and Australia. But there are lots of places in the world that simply do not have the type of soils data that we have in the U.S., and we have a very robust data set. Of course, we disseminate all that information through a couple of different methods. For advanced GIS users, We have the geospatial data gateway and the soil characterization database, where you can actually download the raw data and use that in all types of applications that you may have. And for the general public who are not advanced ArcGIS users, we have Web Soil Survey, which is a fantastic package. It's web-based, and it has a very easy interface for homeowners and landowners to use as they look at their properties. What's nice about having all this out on the internet is we can update this data very easily. It used to be we would print a paper soil survey and print 1,000 copies of those and send them out all over the US, but then when there was an update that was needed, you got to reprint the book and send all of that out there. So obviously having all this out on the internet now is a big advantage. Well, we have all these sensors. We have all this data. We're looking down on it with satellites. We're using these proximal sensors, and we come across an area like this. And so the question I pose to you is, what is limiting the productivity of this soil? Is it a pH problem? Is it salinity? Is there a soil textural issue? Does this have low cation exchange capacity? No organic matter? Is it polluted? Are there multiple problems here? We have no way to figure that out unless we collect soil samples. And that used to be what we did for many years, is collect the soil sample, go back to the lab, and process it through a bunch of chemical and physical processes. And we still do that to some degree. But with these proximal sensors today, what we're able to do is take that equipment on site and make laboratory grade determinations in situ in a matter of seconds, which is a really powerful tool. So PXRF can allow us to answer many different questions simultaneously. Is this soil safe for agricultural use? Or does it have heavy metals in it, for instance, like lead, cadmium, arsenic, that may pose a threat to human health? What factors are limiting its agricultural productivity? What if I was able to scan the soil and acquire all of this different elemental data and then predict multiple parameters off of the same data set, the pH and the salinity and the CEC? What about in a developing area of the world where the country is very poor, they don't have the ability to do a lot of soil testing, and you say, if I only have 1 scoop of fertilizer, that's all I've got. What's the best way that I can apply that fertilizer? Should I spread it equally across the field that's the size of this room? Or should I take that fertilizer and just put it in this part of the field because the rest of the field doesn't need any fertilizer? We have no way of knowing that unless we sample the soil extensively, collect 100 samples or whatever, and send all those off to the lab. Of course, there's no way they're going to be able to pay for that in a developing country. But what if I was able to take the XRF out and literally just scan 60 seconds per spot across the field and give you all that data in a matter of an hour in that particular field? That'd be very powerful. Well, let me take you through how this works. You might think with the name portable X-ray fluorescence, this is a really difficult concept to understand. It's really not. Essentially what happens is the X-ray gun itself looks kind of like a phaser off of Star Trek. Okay? You take this gun and you hold it down on the soil and pull the trigger. It's got a low power X-ray tube inside. The one that I have has a rhodium X-ray tube. It operates from 10 to 40 kiloelectron volts. That's very low power. It's lower power than a dental X-ray, to put that in perspective for you. Okay? As the X-rays come out of the gun, they hit the soil, and when they strike the soil, or any matter for that matter, it ejects an inner shell electron out of the atom, and then an outer shell electron likes to cascade down to fill the inner shell. But in order for this electron in the outer shell to move to the inner shell, it has to give off energy. And that energy is the fluorescence that the detector then reads, and that energy is unique to each element, and the amount of that energy that comes off of those elements gives us an indication of the abundance of that particular element. So there's a couple different methods of doing this. There's what we call energy dispersive analysis and wavelength dispersive analysis. The older XRF units actually used an active radiation source. They actually had americium or something, a little pellet in the gun. We don't have those anymore. Okay, we just use an energized X-ray tube, and it's battery operated instrument. So there it is. That's the gun that I have, and it's Olympus Delta DP6000. There are many different manufacturers who make this type of equipment, at least half a dozen throughout the world. We can operate this on battery power. The battery pack is actually here in the handle. You can scan continuously on one battery for about 4 to 5 hours. So it has a nice battery life, and typically we're in the lab, we just plug it into the outlet and run off of line power. To standardize the instrument, there's a little calibration alloy coin that you scan to start the instrument up. The computer reads that, it knows the composition of that alloy, and it makes sure that it is reporting accurately. And my particular instrument has two modes, one called soil mode, the other is geochem mode. These are basically just packages of different elements that the instrument is configured to read. They have trade-offs. Soil mode does a better job with lower limits of detection. Geochem is more adept at reading a wider number of elements, but you suffer a little bit on the limits of detection. It's not quite as sensitive. So it really kind of depends on what application as to what we will look at. We can get lots of different elements. I'll show you that here in just a second. We do okay with lighter elements, but generally what we find with X-ray fluorescence is the larger the electron cloud, the heavier the element, the farther it is down on the periodic table, the more accurately we can read that. We can get some lighter elements such as phosphorus, aluminum, silicon, but only at really high concentrations at the percentage level really. By the time you're getting down to parts per million accuracy, it's below the limit of detection. So there'll be lots of different applications that I'll talk about with this. Scanning here is totally customizable. I've typically found that scanning at 30 seconds per beam works really well. In soil mode we have 3 beams, in geochem we have 2. So one scan, typically 60 to 90 seconds for the entire package of elements, and that works really well. You can scan as long as you want. You could do 10 minutes per sample, but then you're really using or losing the alacrity of the instrument, which is one of its major benefits. And as my instrument is configured with the portable test stand and whatnot, it costs about $40,000. One of the nice things about this kind of equipment is you can rent it. You don't have to purchase it. So if you have a research study that you just want to use it for a couple of days or whatever, they'll literally ship it to you in a Pelican case, FedEx. You can pull it out and use it, and it's like $500 a day, something like that. But there's lots of companies out there who rent this type of equipment. Here's the periodic table. What this is essentially showing you is those limits of detection. Notice for magnesium, aluminum, and silicon, we can get those around 1% and higher. Okay? By the time we get to phosphorus, we're down to 0.5%. Sulfur and chlorine, we're starting to get down to 200 parts per million. But by the time we get to a lot of our heavier elements, we're on the order of limits of detection of 5 to 10 parts per million. Another big advantage of XRF is the wide dynamic range. When you do elemental quantification using inductively coupled plasma atomic emission spectroscopy, you are digesting that with an acid. You calibrate your instrument for a certain range, but if your assay happens to be above that range, you have to go back and do a dilution and rerun it again. You don't have to do anything like that with XRF. I might scan one sample and it might have 250 parts per million calcium, and the next sample that I scan might have 27%. Okay? So you can do it just like that, one sample to the next. There are several referenced methods available for the use of PXRF for soils analysis. One of those that's most widely cited is EPA method 6200. This came out in 2007 in February, and it is PXRF spectrometry for the determination of elemental concentrations in soil and sediment. The NRCS, which is a branch of the U.S. Department of Agriculture, has a referenced method for this in their Soil Survey Field and Laboratory Methods Manual that came out in 2014. And most recently, the new Methods of Soil Analysis by the Soil Science Society of America also have a method for that as well. So there are lots of potential applications in soil science, and I'll talk about those. Textural determination, pH salinity, CEC, base saturation percentage with an asterisk. I'll explain that in just a second. Plant essential elements, potentially mineralogy, differences between soils. The real advantages of this technique are it's non-destructive. So think about that. When you do an ICP analysis, you actually dissolve some soil in acid. You don't have to do that with XRF. You can literally scan it and then put it right back on the shelf. If you're doing forensics analysis, where you're looking at some kind of an issue like that, preservation of samples is key, and that's really important. It's rapid, 60 to 90 seconds, multi-elemental, which is a big advantage over labs which are still using atomic absorption, which only uses provides one or two elements at a time. Low limits of detection with wide dynamic range. The disadvantages to this technique: no hydrogen, carbon, or sodium. Now that's a problem when we do things like base saturation percentage, although Dr. Galbraith was telling me yesterday, here on the East Coast, you really don't have to worry about sodium because you don't even have to, have much of that. But out in West Texas, that is a concern. We have a potential way to get around that using chlorine as a proxy for sodium because they tend to associate as halite so frequently. You might say, well, how do we get pH if we can't determine hydrogen content? I'll explain that here in just a minute. There are some moisture effects that you have to be concerned with XRF. Generally, the literature says when soil moisture is above 15%, there is some attenuation of the signal that needs to be considered, and we typically apply a moisture correction factor to deal with that. It's not to say you won't get a reading above 15%. It'll just be not as accurate a reading as you would have if the soil was dry. And then soil heterogeneity. Realize that soils are inherently heterogeneous. In our area of the world, we have lots of little pockets of calcium carbonate masses or iron manganese concretions and those kinds of things. Realize that the aperture of the PXRF is about the size of a nickel, okay? And if you happen to place that on top of an iron manganese concretion and scan it, you're going to get a lot of iron and a lot of manganese. But then if you move over literally 2 centimeters and scan it again, you'll get a wildly different reading. That doesn't mean the instrument isn't performing accurately. What it means is the soil is just that variable on a very small scale. So what we typically do in my lab to account for some of these, if we need to do the scanning in the field, we can. It's obviously field portable. But a lot of times we collect the sample, bring it back to the lab, we dry it first, and then we grind the soil. And by grinding the soil, we tend to homogenize it as much as possible. And that does help to offset some of these potential impacts. Well, let's first talk about soil salinity through X-ray fluorescence. Now, we know excess soil salinity can degrade soil quality and promote desertification. And realize that salts are just commonly combinations of various different elements: calcium, magnesium, potassium, sodium, sulfate, chloride, carbonate, bicarbonate, those kinds of things. All those elements in green we can read with XRF. So we can't do a perfect job of telling you every element in the salt, but we can give you some information. Realize that traditional methods of determining soil salinity involve us making saturated pastes or doing some kind of a slurry, like a 1-to-2 soil to water slurry. And then we use electrical conductance, and we look at how much electricity is conveyed between 2 electrodes. While this is an accurate technique, it doesn't tell us anything about which elements are causing that electrical conductivity. This is also kind of a laborious process, typically performed ex-situ, and again, you don't know anything about the type of salt present. So to take a look at this, we collected 121 soil samples across 3 different Louisiana parishes. This was back a few years ago when I was on the faculty at LSU. We made elemental determinations by PXRF scanning. Following saturation, we looked at saturated paste conductance using a Model 4063 digital conductance meter. And this had a wide salinity range, everything from 0.11 to almost 80 decisiemens per meter. Remember or realize that a saline soil has a conductance of 4 decisiemens per meter. So some of these are what we consider to be hypersaline soils. And we simply looked at the relationship between electrical conductance and our predicted electrical conductance using different linear regression techniques. Using simple linear regression, where we were only looking at one element like chlorine, we got a really nice R-square of 0.83. We used multiple linear regression and we were using different elements in addition to chlorine, like calcium and other things, we could get that R-square up to 0.90. Now our validation R-squares were 0.77, 0.70, not perfect, not as good as ICP. I'm not here to make that argument. But again, it gives us an idea of what we're looking at in the field in 60 seconds. And that's a pretty powerful predictive technique. So we concluded that soil salinity can be reasonably inferred using PXRF elemental data as a proxy. And this elemental data allows for the identification of some salts. If you're looking at sylvite, it's potassium chloride. I can tell you exactly what that is. If you're looking at halite, sodium chloride, I can tell you about the chlorine component, just not the sodium. All right? But this elemental data can be used to predict multiple soil parameters, and that's also one of the powers of using portable X-ray fluorescence. If you're interested in this publication, it was back in 2014 in the journal Soil Science. Well, since we looked at soil salinity and it worked pretty well, we thought, why not look at the water directly? And the first time we opened this can of worms, I have to tell you, we started looking in the literature to see what work had been done using X-ray fluorescence to look at water, and we found one paper worldwide. I mean, I dug and dug and dug, and I just couldn't find anything out there that had been done in this area. So this was really some cutting-edge work that was done just in the last year or so. Now, we've talked about the fact that this type of salt present cannot be identified by traditional electrical conductance, so that's why we decided to go with the X-ray fluorescence. Again, a little bit less accurate than ICP or atomic absorption, but you can do it in situ. And one thing that I pointed out in other venues is XRF gives you the ability to differentiate remarkable from non-remarkable samples. So the way that I would explain that to you is if we put a water sample or a soil sample in every chair in this room, and I took a couple of drops of arsenic and I put it in one sample, and I said, find the sample that has arsenic, the only way you'd be able to do that is to run every one of those through ICP, and those are $50 a pop. Or I could come through with the XRF and I could say, that's the one right there that has the arsenic. And once you know which sample has the arsenic, then you could just run that one sample on ICP. So it would save you a lot of production time and money doing things that way. When we talk about looking at salinity in water, this wasn't the ultimate goal. This was our we got to kind of crawl before we walk step. We eventually wanted to get to the point where we're testing metals or pollutants in water. But before we got there, we said, let's just take something simple like salt in water and see if it would work. So to do this, my team collected 256 samples from 10 countries and across 15 US states. Most of the time when we do any type of work in our lab, we split our data set into a 70% calibration data set for creating the predictive model, and then a 30% independent validation data set, which we then use to test the performance of the model. We looked at the salinity through XRF, digital salinity bridge, and also ran all of these water samples on ICP. And this is how we prepared the water samples in the lab. We used these little sample cups. These hold exactly 14 milliliters of water each, and they're just little plastic cups. Then on top of those, we put this special piece of plastic, and this is what's called a Prolene thin film. It is a special type of polymer that is used especially for X-ray fluorescence work because it allows for maximum X-ray fluorescence transmissivity. It's not going to degrade that signal. Believe me, we had to learn this the hard way. A few years ago when we were working with some soil samples, we were scanning them through Ziploc bags, and we said, wow, we're getting a lot of these elements. It looks really great. And then I was thinking, gosh, plastic. And we started scanning the plastic bags, and we got all kinds of chlorine readings and stuff. So we learned the hard way that we got to really be careful of that. So anyway, we put the water samples in these little cups. This is what we call a hooded test stand. And we just mount the gun inside the hooded test stand, and there's a flat stage in here that has an opening just like that. You just take the water cup and set it right on top, close the hood, and that way when you engage the X-rays, you're not irradiating yourself, and you certainly don't want to do that. So what we found is a validation R-square predicting the salinity at a rate of around 77%. Again, not perfect, but pretty good for 66 or 60 seconds for something that we could do in the field. Because we got these kinds of results, we were very encouraged that, man, maybe this really would work with water and heavy metals. Let's take a look at that. So what we decided to do is take a look at some ICP standards. And this really kind of came into focus, the importance of it, when we had the Flint water crisis, and they had all kinds of lead in the water there, right? So what we did is we just literally took some ICP standards off the shelf, and these had a certified reference value on the bottle of 998 parts per million. And when we scanned those with XRF, we got 981, 962, and 958. Again, not perfect, but really good to be able to do it in 60 seconds in the field. So we were thinking, man, we've got to do a research project on that, and that's what we have underway right now. You see the kinds of coatings that you see on the insides of pipes. I mean, there are lots of different things that are in our water, lots of different elements. Many of those are benign. We don't need to worry about them. But some of them we do need to be cognizant of, and that's something for us to consider with X-ray fluorescence. So I really have to give a shout out to Delana Pearson. She is an undergraduate student, a non-traditional student from Canada, is on my soils judging team. but she did this work on the salinity of these water samples as an undergraduate research project, and her very first publication was in the Journal of Hydrology, which I think has an impact factor around 4. So she really did a fantastic job. So now she's doing a follow-up study on 360 metal-laden samples in water that we got from mining sites in South Africa. And we're literally chugging through that data right now as we speak. Well, let's talk about another area where we have metals in water. Some of you might recall the Gold King mine spill. This was a spill that released an estimated 3 million gallons of metal-laden sludge into the Animas River. Arsenic, lead, cadmium, copper, iron were some of the metals of concern. Of course, these metals are cations, and they like to bind to negatively charged clay particles and then float down the river in suspension. The metals move with them in suspension, and the spill happened right up here north of Silverton and moved all the way down past Durango, Aztec, Farmington, and this is the area that we specifically looked at. There's a lot of agricultural production in that area, specifically alfalfa. Well, August 5th was when we had that oops kind of moment, and I want to just show you what that looks like. You're about to see just an environmental disaster unfold before your eyes. They were kind of digging back into the side of the hill, and there you see the water just starting to leak out a little bit. Doesn't look like it's going to be that big of a problem to deal with. Then it really starts to flow out of the side of the hill.
We're digging really high. Is he going to go close it out? What do we do now?
What do we do now? Okay.
Get a little video of this, I suppose.
Not sure what was being said there.
I know, we were about 20 feet off.
But realize all of this has got all kinds of metal in it, okay? And it's washing right down the side of the hill into the Animas River. Look at that. Okay? Yeah. Yeah. So, you get the idea, all right? Let's see. Following all the way down the river. All right, let me just move this ahead over here. Okay, so this is what the river looked like before. This is what happened during the river. It just turned the entire thing brown, okay? And realize that they use water out of this river for irrigation. Now, luckily, the guys downstream in New Mexico knew this was coming, and so they shut off all of their irrigation ditches. So the big plume of this nasty colored water moved past the irrigation ditches, and it didn't impact them directly. But they can't keep those shut forever. And, you know, a lot of the sludge was deposited on the riverbanks and on the bottom of the river, that sort of thing. So now that they've opened those irrigation ditches back up, what they're worried about is small accumulations of those metal over time as that material continues to work its way down the river, okay? So when we went over there September 1st through the 3rd, you know, I got a call from the NRCS, and they said, man, Weindorf, we need you on site with your X-ray equipment right now. So we went over there immediately and started scanning. We looked at 4 different types of land conditions. Control soils that are not irrigated. These are kind of in the upland positions, you know, on the back slopes or foot slopes where they're not even irrigated, okay? Then we looked at irrigated farm fields. Then we looked at riverbank sediment, and then actually we found a reddish-orange sludge on the riverbank, and we were able to scan that as well. We did 140 samples up and down the riverbank in 3 days, and here's some of that scanning occurring on site. You know, here's some alfalfa production that you have down here, some alluvium down in the river itself, and there's that reddish sludge that we found along the riverbank, and we're actually scanning that. Here we are looking at one of those closed-off irrigation ditches. The Navajo Nation, of course, is very concerned about this. These are some of their lands that they use for producing pumpkins and watermelons and things like that, irrigation. Here's the intake to one of those irrigation ditches. And this is the real concern. You see the color of that water. It's not blue. It's not clear. It has lots of suspended sediment in there. Okay. So here we are scanning more of that sludge. This is up near Durango, Colorado. Here we are giving the sludge the middle finger salute. And you can see, you know, how it's impacted this entire area. This is what I want to show you here. So these are our different types of soils: the control soil, the irrigated soil, the riverbank, and the riverbank sludge. I want you to look at the averages that we saw for iron, for copper, zinc, arsenic, and lead. In every instance, these increased from control to irrigated to riverbank to actual sludge. And by the time we got down here to lead, we got an average reading of 637 for the sludge itself. That exceeds the EPA residential screening limit for lead, which is capped at 400 parts per million. So this is something to be concerned about. Now, I will tell you, in the work that I've done around the world, I've actually found levels a lot higher than that in some places. But it is something that we need to be concerned about. What the farmers in this area are worried about is, are they going to be able to sell their crops? You know, the people who buy those watermelons from them and that alfalfa, hey, they know it comes from, you know, the Animas River Valley there north of Farmington. Well, all of a sudden they hear about a spill like this and then no one wants to buy their commodities. So there's a real economic impact of this. So the concern moving forward is that that sludge will be resuspended in the river, then pumped out of the river for irrigation purposes into these ditches, and that's how it will continue to work its way onto the land. How could this potentially happen? Think about hydrologic pulses. A rapid snow melt in the spring, severe thunderstorm, you know, in a catchment where you get a lot of flood water coming down. When you get those types of flood waters occurring, that's when the sediment will be resuspended. Well, I had a really salient moment in doing this research study when I'm driving back to the hotel one night with the data that we had collected, and my cell phone rings, and I'm looking at the caller ID, and it literally said Congress. I'm not making that up. I'd never seen that before, right? And so as it turns out, the Bureau of Indian Affairs there had heard about some of the work that we were doing. You know, we were on the front page of the local newspaper with some of the scanning work we'd done, and they said, we would like to have you come to Washington, D.C. and testify in front of Congress as it relates to the spill. And Gina McCarthy sat right next to me, and we had John McCain about 20 feet in front of me, and I mean, he absolutely grilled her over. I want a name. I want to know who caused this to happen. Da, 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 da. You know, she's sitting there saying, what do you want me to tell you? It was Bob on the backhoe. That's the guy that actually caused it to happen. I mean, you know, he nicked it a little deeper than he should have, but he makes $10 an hour, you know, like we were trying to do the right thing and clean up the spill site, and there was a mistake that happened. But it was a really interesting moment to go through that entire process and provide some testimony. So what about pH and PXRF? Now, I mentioned to you that hydrogen is way too small, way too stable for us to get this fluorescence radiation. So how could we possibly determine pH using X-ray fluorescence? Well, realize in soil systems that alkaline soils typically have an abundance of calcium and magnesium. And acidic soils typically have quite a bit of aluminum and iron. So all of those different elements right there we can read using XRF. And we can use that elemental data as a proxy or a predictor for pH. And you might say, well, why not just go ahead and insert your normal, you know, electrode, pH electrode, and determine pH that way? And that's fine if you can do that. But what do you do with the frozen soil, like this permafrost? What do you do with a lithified soil horizon, like a petrocalcic, a petrogypsic, a petroferric contact? What about historical samples that are literally mounted on the wall in the hallway of your building as a monolith, and they might have been collected 70 years ago? How could you determine the pH of those soils when they're mounted as a museum exhibit? You couldn't do that with a pH electrode in the traditional sense, but I could scan that monolith right on the wall with an XRF and predict the pH off of it that way. So we had 639 samples that we collected, evaluated them through standard methods, saturated paste, electrode, that sort of thing, and X-ray fluorescence. Using our multiple linear regression predictive equation, you see we get an R-square of around 77 with a root mean square error of 0.68. Akriti Sharma published this paper back in 2014 in Geoderma, and I'd encourage you to take a look at that for these unique applications. Now, she did a follow-up study on cation exchange capacity. If you've ever had to do this in soils, it is a pain in the ass, big time. You're talking about doing all kinds of rinsing of the soil back and forth, sodium acetate, and then rinsing with ethanol, and then coming back with ammonium acetate, multiple rinses. You'll work all day and you'll get 20 samples done, okay? And it is an accurate way to do it, but it really takes a lot of time. It's very laborious. So we thought, man, we can get a lot of these elements, especially our plant essential elements, and all of those are cations, right? They're all represented within cation exchange capacity. We have several different methods for doing CEC determination in the lab, but these are not field portable. So here we had 360 soils that we evaluated, again, using the ammonium acetate method and PXRF. Here we got an R-square of almost 0.91. So really strong results. And again, Akriti Sharma, my master's student, published this in Geoderma. This was in 2015, if you're interested in taking a look at that paper. Well, what about some issues that we might have out in West Texas? You know, if I was to show you this gypsic soil here, a leptic haplogypsid or a calcic argigypsid, and I was to say, can you identify for me the different horizons that are in this profile? Well, Galbraith would know how to do that. He could probably do it with his eyes closed, okay? But for those of us like myself who are a little bit more challenged in that aspect, I would have a hard time picking these out. I mean, I'd really have to get in there and look at it carefully. As it turns out, there's actually a wide variation in the gypsum in this profile. You might have 40% here and 65% here. But you can't see it because visually it all just looks like a white powder, okay? But what if we were able to actually scan up and down that entire profile and look at elemental data as a way to differentiate different soil horizons? The early versions of portable X-ray fluorescence did not have very good sensitivity for sulfur. So we had to use calcium as a proxy for gypsum. But that was a problem because you also commonly have calcium carbonate co-precipitated with calcium sulfate. But with the advances that we've had in this technology, with now the DP6000 model of the instrument, they have much greater sensitivity for sulfur. So I can literally scan the sulfur signature, put that in a predictive equation, and I get an R-square there of 91%, as compared to other gypsum determination methods like thermogravimetry or acetone precipitation. Okay? So you can either use sulfur independently, or you can put these elements, several elements in a multiple linear regression, use sulfur and calcium to predict your gypsum content. I've got several publications on this, the most recent of which was 2013 in the Soil Science Society of America journal. Prior to that, we did some kind of laboratory-based determinations, and these were both published in Soil Science back in 2009. Well, now I got to get to this last project here. This is one that's currently under peer review right now, and this is calcium carbonate stage development. Secondary calcium carbonate is common in arid and semi-arid lands worldwide. These are expressed as BK, BKK, BKM, or BKKM, or even CK horizons in various stages of development or accumulation. And these are kind of morphologically established qualitative stages that go from stage 1 through stage 6. Now, there are different methods that we can use for lab quantification of calcium carbonate content, titration or pressure calcimeter, which is gasometry, but those really aren't field portable. You kind of have to do those in the lab. So this just kind of shows you what some of these carbonates might look like. These are some stage 1 carbonates that we identified in Denver County, Colorado. This is a stage 5 petrocalcic horizon with pissoliths in Lubbock County, Texas. So this is a very common subsoil, right outside our neck of the woods in Lubbock. I don't guess we actually have woods in Lubbock, but if we did, that's what the soils would look like. So what we commonly use right now is this kind of qualitative chart that is in the field manual for describing and sampling soils. And so you look at this and you can kind of see the different stages. Here you start to get a complete horizon forming, then you get some of these laminar coatings on the top. You get some brecciation occurring in here, the formation of pissoliths and other things. We use this chart to just kind of qualitatively look at the soil and say, I think it's a stage 2 or stage 3. These are the same kind of figures for coarse fragment matrix, where you tend to get some carbonates accumulating on the lower half of different cobbles and aggregates within the soil. And we've seen some really good examples of this in New Mexico. So the question we posed is there a correlation between the developmental stage and calcium content? And if so, can X-ray fluorescence be useful in helping to determine the developmental stage? So to answer this question, we collected 75 samples across 4 states, Texas, New Mexico, Colorado, and Kansas. We had all 6 developmental stages represented. We scanned these soils as 2 different conditions, intact aggregates, and then we also ground those intact aggregates to form a sub 2 millimeter fraction and scan the powders. And then all of the developmental stages of these different aggregates, before we ground them up obviously, were determined by a panel of 5 experienced pedologists working with the NRCS soil survey staff. So what we did is we related PXRF determined calcium carbonate content to secondary carbonate developmental stages determined by that group of 5 panelists. And this is what we found. With each successive stage, as you look at the various quartiles here in the medians, you see the calcium carbonate content increases up to a point where there's not much difference between stage 5 and 6 as intact aggregates. I want to also point out to you that the widest variation was found in stage 3. That was also rather interesting. If we look at what happened with the powders, the same sort of situation presented itself. We have these carbonates, the amount of calcium rather, increasing with developmental stage, stages 1 through 5. But again, stage 5 and 6 don't differ that much, and stage 3 has one of the widest variations. So all of this was good information. So what we actually came up with were some rules that we have developed, and we put these in the publication that we're working on, that help us use this X-ray fluorescence calcium data to help determine, should it be a stage 3 or 4, or where should we be? So what was an interesting finding was the panelists only unanimously agreed on 22.6% of the samples. Now realize these were evaluated ex situ. We feel like if they were to evaluate them in the soil profile, they probably would have had a better understanding of what was going on there. We literally just put them in a little bucket and brought them to their office and asked them to evaluate them. But still, only 22% of the time did all 5 panelists agree. This shows you that even amongst experienced people, there's considerable disagreement. There wasn't much difference observed in stage 5 and 6. Mineralogy, as confirmed by X-ray diffraction, showed a wider diversity of mineralogy at lower developmental stages, and the widest stage variation for calcium content was again found in stage 3. I've got to give a huge shout out to my co-author on this project, my daughter, Camille Weindorf. This was her 8th grade science project. And she went to the regional science fair, and out of 500 kids got 1st place. So I was pretty stoked about that. And so we definitely put her in as a co-author, because all of this work was done in my garage, literally, with her working with the instrument, okay? So there's been some other works that I've published. If you go out there and Google this, characterization of podzolic horizons, evaluation of heavy metals in compost. I did a project on lithologic discontinuities in Texas, Hungary, and Italy. We've looked at enhanced pedon horizonation using X-ray fluorescence. I want to quickly point out some of this work on heavy metals in Zlatna and Kopshamica, Romania. These types of areas like this in Romania are not cordoned off. They're not fenced off in any way, shape, or form. You can literally walk right up to this area, and we saw kids playing around in areas like that. This would be a super fun site in the U.S., okay? And remember, I pointed out to you those health limits established in the literature that say if you have a limit of an element at a certain level above that, there's a health threat. In Romania, the action limit for lead contamination in soils is set at 100 parts per million. We measured the lead at this site at 38,000 parts per million. And not only are they allowing people to walk and crawl all over these types of sites, there were farmers in this area, just to the right of this picture, growing potatoes in the polluted soil that they're feeding to their animals and they're feeding to their families. Here you see a guy right here fishing in this pond, right outside this petrochemical plant over here, okay? We went on to a playground. We found cadmium right underneath the swing set where the little girl was playing at 120 parts per million when the health limit is 5 parts per million. So these people have no idea what kind of danger they're in. And with X-ray fluorescence, we could literally go up and down this valley, scan 100 points in a day, pull all of that information into ArcGIS and Kriegit, and produce a spatial variability map like this in a single day sitting in a pickup truck. Okay? So that's the power of this kind of technique, really, as we move forward. If you're interested in any of those publications, these are some of those that I have. Kind of a pilot study right now in International Journal of Bioresource Science, and then geoderma and environmental pollution. And John, you wanted to mention a couple of projects that you have also on that. Let me just let you, step up and say those, and then I'll have a few last comments to wrap up.
All right, thank you, David. So to illustrate how simple this technology is, I have actually borrowed David's machine several times, or I have collected samples and sent them to him. And just some examples are, I actually had a representative from the company come out to teach me how to use the machine. And as we did, we started on Strubles Creek before it reaches campus, and then just tracked it down all the way to the duck pond, and then passed just to see if anything showed up. And when we crossed Price's Fork Road, just on the other side of Price's Fork Road, we hit a big spike in nickel and zinc. And so I thought to myself, I looked right up the hill and I was thinking pollution coming from the coal plant. But we found it nowhere further downstream at all, even 15 feet further downstream. We were right next to the road, and so we think this was coming off the car tires of the road. Interesting little exercise that took about 3 hours. And then a second project that we did, Eric Severson just completed his PhD study, and one of his questions was, is there a lithologic discontinuity between the upper parts of his profile and the lower parts? And he measured, he did zircon to titanium ratios through the soil. Unfortunately, he didn't include that in his dissertation, but he did get positive results on the one profile that he did. The only reason he didn't include that is because he only did it on one profile. Now he could go back and follow that up, and he did all of that. I actually did the scans for him in about an hour in the lab, so no problem with that. I took the gun, David's gun, to Nepal. Carried it on the airplane, carried it through the airport, no problems checking it in or out. Used it in Nepal. They were concerned about the fact that there were rock crushing plants trying to make aggregate out of rock, pulling rock out of the river, crushing it, and then selling it. But the powdery residue, they were dumping right back into the river, and the local citizens near Hathalda were very concerned that they were releasing, that there were metals in the rock that might be polluting their drinking water. And of course, they use it for irrigation as well. And after sampling that, as we did that on a study abroad program, and we worked with the scientists at the University of Tribhuvan, it's hard to pronounce, Tribhuvan University at Hathalda, and they concluded that there was no risk after we sampled soils up and down the river coming off of these plants. And then also, I had an undergraduate student, Caitlin Heron, and she just finished an undergraduate research project, and she collected samples near the Fort McKenzie area where the tar sands are being mined. And she brought those samples back to Virginia Tech, and we scanned all of those because her working hypothesis was that the processing at the tar sands to prepare the material to go into the pipeline to come south toward the U.S. were releasing contamination. So she studied a variety of sites down the prevailing wind direction from that plant, and actually did not detect any noticeable pollution, which was interesting. But they did notice an effect on the plant life near the plant. As it turns out, and she sampled that, and it was upwind of the plant. As it turns, it was downwind from a major railroad line. And so they were bringing materials in and out of Fort McKenzie, and so the actual pollution was from the railroad, not from the mine. But that was a simple undergraduate research project, and it just illustrates some examples of what can be done. I can see where this can be extrapolated into forestry, into anybody who's studying water quality, depending on the element that you're looking at. So just a few experiences that we've had here at Virginia Tech. I sure wish we had one of these.
So one lesson that I learned when you travel with the instrument is when you go through security at the airport, you never call it an XRF gun, right? It's an XRF spectrometer. So I told you about the calcium carbonate developmental stage. These are kind of some other projects that we're looking at right now. The metal-laden waters, again, we're using leachate that we collected from mining sites in South Africa. We have a project this summer that we're going to be working on in Romania looking at phytoremediation effectiveness, where we have certain types of plants that differentially extract heavy metals from the soil. We want to try to scan the vegetation and see if we can detect how much metal has been pulled out of the soil there. Looking at plant essential nutrient assessment, are there deficiencies or toxicity issues that we could detect in vegetation? The environmental threat from mine tailings, this again is in South Africa, the Eleazar mine. You see these huge tailings piles, and the problem that they have there is reestablishing vegetation on these. If you don't get vegetation reestablished, when the wind blows, all this mine tailing, which still has lots of uranium and gold and other things in it, can blow off into the rangeland and cause problems for the animals grazing there. I have a master's student who recently finished a project characterizing pharmaceuticals using X-ray fluorescence combined with Vizsnir spectroscopy. And that was a really neat project. It's currently under peer review at Forensic Science International, and we're waiting to hear the results of that. But the idea was not to stop with aspirin and antacid tablets. The idea is if the proof of concept works with medications, would the same proof of concept work for illicit narcotics? So when you see some kind of white powder show up at the airport security screening, would we be able to scan those and get some kind of a profile on what type of narcotic that is? We're also looking at temporal shifts in soil properties. Again, thinking about monoliths that you have mounted on the wall that were collected 50 years ago, and then going back to those same locations where they were collected today and looking at the changes in soil properties over time. If you're interested in kind of an overview of X-ray fluorescence as it applies to soils in general, I would point you to Advances in Agronomy back in 2014, a paper that I published with Nora Backer and Yuanda Zhu. But this is kind of a good overall review of X-ray fluorescence and where the technology stands. In conclusion, I'll simply point out that years ago when we did soils analysis, we didn't have these types of tools. This young man right here is my grandfather, and he was a soil conservationist out in eastern New Mexico. He could not have possibly imagined that I would have an X-ray gun and be sampling and scanning soils in China, decades later, following in his footsteps. So this type of instrumentation gives us quality, quantitative data in the field in seconds with multiple applications. We've talked about its advantages, the alacrity, portability, non-destructiveness, on and on and on, minimal to no consumables. You're seeing this adopted widespread now all over the world. Lots of different countries that are getting into this. I always encourage people when I give this talk to shift the paradigm from testing this technology to just using it. We have a dozen reference methods and journals and professional organizations all over the world. There are hundreds of papers that have now been published. It works. We just need to now start using it more widely for all kinds of applications, and I think you'll see that continuing throughout the years to come. So with that, I will wrap up and say thank you for the time, and I'd be glad to take any questions you may have.